Let's talk about expectations of functions, moments, and moment-generating functions. We've already talked about these things before, especially in the context of discrete random variables. Let's now talk about them in the case of continuous random variables. So let's let g be a function. This is g of dot, g of whatever, be a function from the reals to the reals. Then for a random variable x, we have that the expected value of g of x is, well, depends, I guess. If x is discrete, this is just the weighted average of this is little x, of g evaluated at x. There's a probability that x is, well, x, right? It's just the weighted average of all these g of x's. This is if x is a discrete random variable. On the other hand, if it's continuous, it's the integral over the reals of g of x times the density function of x. Okay, if x is continuous. Right. So, and as we saw before with the discrete random variables, the kth moment of x about some mark a on the real line, some number a, is defined to be this. Okay, it's just the expected value of x minus a raised to the kth power, and this will be, again, if this is discrete, you could write it as the sum like this, right? Using this result up here, if my function here is g of x equals x minus a raised to the kth, I use that, right? So I'm just averaging, I'm taking a weighted average of all these kth deviations, or deviations raised to the kth power, right? Or in the case of, if they're discrete, it's going to be the integral over the reals of x minus a to the kth, but now times the density function of x dx. This is if discrete, if continuous. Okay. All right. Also, as before, the kth moment about 0 of x, or simply the kth moment If we say the kth moment, we actually mean the kth moment about 0. Right? It's just the expected value of x minus 0 raised to the kth, or which simplifies to the expected value of x to the kth power. Okay? Good. And again, so these moments are real important, and they sort of describe the behavior, the average deviation, in a sense, of a random variable about a point on the real line. And oftentimes we want to discuss in particular, say, the variance of a random variable, which is essentially it's just the second moment about the mean, which describes how the random variable tends to deviate on the average from its average, from its mean, from its center of mass, right? So the variance of x is defined to be the expected value of x minus the expected value of x squared, right? Which, as before, we can get that inside-outside formula. It's the second moment minus the square of the first moment, right? Okay, and so this, so you could actually write the variance then as this. You could write it like this if you like. It's the chance, then minus the square of the first moment, right? This is if x is discrete. Or if it's continuous, if x is a continuous random variable, it's the integral over the reals of x squared f sub x of x dx minus square of the mean, which can be written like this, right? If continuous. Okay. Now, let's talk a little bit about moment generating functions. We've